Today's complex systems require advanced engineering processes, but are often carried out by environments that struggle to keep up with the complexity of those systems. Such environments are usually a mixture of siloed engineering tools, such as requirements tools, model-based system engineering tools, verification and validation tools, and discipline-specific tools, such as hardware and software development tools, and are very commonly dominated by text documents. These kinds of siloed environments provide major challenges in maintaining consistency of the engineering artifacts and effective decision-making. The result is that engineering of such products is much more costly and time-consuming than it needs to be. What we need is an environment that integrates the different engineering tools, data and processes into a digital fabric that enables engineering data management, traceability, data consistency and analytics to support decision-making. Such an environment should also be open and standards-based to allow seamless integration of tools whilst preventing vendor lock-in. To ensure the validity of the data across the engineering process, data should be managed in the trusted tools that author it and not copied or duplicated between tools. The answer? An open, standards-based federated approach to connected data across engineering disciplines, enabling collaboration and cross-lifecycle insights and analytics. The IBM Engineering Lifecycle Management Platform, or ELM, offers a set of capabilities to integrate, manage and analyze lifecycle data across all applications and tools, and is based on the Open Services for Lifecycle Collaboration standard, known as OSLC. ELM also provides a set of lifecycle applications for requirements management, design management, test management, and tracking and planning that are seamlessly integrated into the platform. The open nature of the platform means that users are not confined to these applications. Let's now look at how the capabilities of the ELM platform enable the integration of engineering data across multiple providers into a digital thread that supports data connectivity, integrity, and analytics. First, let's look at data traceability. Links may be made between engineering artifacts in different applications using standard OSLC linking services. Here, for example, we're creating a link between a requirement in IBM Requirements Management and a story in Jira that implements it. And here, we're creating a link between a scenario depicted as a sequence diagram in IBM Model Management and a test case that validates it. When something changes, link validity gives a clear indication of where analysis work has to be done, ensuring consistency of the data across the digital thread. Each one of the tools in the engineering lifecycle may manage its own set of data configurations, but those need to be orchestrated into a coherent set that describe a particular milestone or variant. This is achieved by Global Configuration Management, or GCM. GCM acts as a central catalogue for the data, where the different data providers are organised in a hierarchical manner that represents the logical structure of the data. GCM also allows baselining of all of the lifecycle data with a single click. From that GCM structure, we can easily navigate into any of the data providers, and global configurations ensure that as engineers work across different engineering tools, they are working in a consistent context. Engineering processes need to be specified and enacted to make sure that the actual engineering activities are well integrated into the data. Engineering Workflow Management, or EWM, enables continuous planning and tracking of work as required by agile processes, with tight connectivity to the engineering artifacts in the various lifecycle applications. EWM also supports a rich set of agile planning views, such as Kanban boards and this WSJF ranked list view. Engineering Insights provides a holistic view across all of the engineering lifecycle data, where all of the artifacts and their relationships can be explored and analysed, allowing complex, time-consuming tasks like impact analysis to be performed in minutes instead of months. This view, for example, shows all of the requirements, design and test artifacts across the lifecycle impacted by this change request. And this is not just a pretty picture, this is live data, and we can easily navigate to any of those artifacts from this view. ELM allows live, self-serve reports on all of the engineering lifecycle data, improving predictability and enabling rapid, fact-based decision-making. Such reports can be easily exposed onto dashboards, providing easy access to the most important information for each stakeholder. ELM also provides automated support of compliance evidence reporting. Here, for example, are a set of reports covering the traceability required by the DO 178B standard, such as high-level requirements to test case traceability. IBM Engineering Lifecycle Management, based on OSLC, integrates lifecycle tools into a digital fabric that facilitates efficient engineering by enabling digital connectivity, global configuration management, and process enactment, whilst providing transparency and reportability across the lifecycle.